So you're already getting the idea. Matching in labor markets is like getting married. It really is. Okay, and don't forget that. It's really important. Welcome to today's lecture. Today we're going to talk about the Morton and Pisker model, which is the next level of developing the idea of search and matching in a model where workers and firms are searching for each other, or in this case, passively engaged in some sort of matching process. I hesitate to call it true search because we don't have any rejections in this model yet. It's still a model about just encounters. It's like going to the club and just randomly bumping into people, and later on we'll talk about the giving agents the ability to reject encounters. So you bump into somebody, nah, not for me, you keep on going. In the model we had last week, as Thomas probably told you, and as the model we'll consider today, there are no rejections. The model is cooked to rule out rejections. But it doesn't mean you can't make the model fancier to include rejections, and later on we'll do that, as I said. The nice thing about the Morton Pisker model is it's kind of like the next level from Pisker, but it still doesn't give you the full set of possible margins that agents can act on, and still gives you a lot of intuition. So that's the point of today's lecture. So we'll do a double review. I know Thomas has gone through this already. I'll do it again, and I'll give you some notational tips because a few symbols are different, slightly different. If you look at the Pisker book, that's not one of the things we have to learn to do in economics is to think in terms of concepts. Symbols can change. Unfortunately, we haven't reached the steady state of having a set of symbols that everyone agrees on. So part of the model is based on earlier papers by Pisker and not his book. But that shouldn't impair you from being able to be creative and adapt, okay? It's important. So we're going to go through that model again. I'm going to give you some critiques, and I'd like to get your opinion on this, why you think the model is good or bad. I mean, believe it or not, it was extremely important in the 1990s and 1980s even, inspired a lot of interest, and it got Morton and Pisker the Nobel Prize. Morton and Pisker hooked up in the 1990s and started thinking about this in tandem. Dale Mortenson is an expert, or was an expert on search theory, and wrote some pioneering papers in the 1970s. And when they got together, they cooked up this model that we're going to discuss. I'm going to give you a very, very extensive version of this model, and in the section, Thomas is going to set a lot of these parameters equal to 0. So we'll get the fancy version that can be used in policy, and then it has been and it can be, and we'll have a version that's kind of for sitting at home and playing around with it, getting the feel of it. Okay, so, and then of course there's always a good reason to critique any model, because models are by construction limitations of our view of the world, because we shut down certain things so we can explore the importance of others. So we'll have to ask that hard question, and a good economist always has a good criticism of every model. It means you really deeply understand when you've shut down some mechanism, you can always come back and say, well, yeah, we did actually not consider that, and I'm going to maybe even claim that doesn't matter much. Okay, maybe it does matter. Okay, so we'll see whether those critiques actually hold water or not. Okay, so last time we had the Pisker model. I'll take you through that again. It's based on this notion of the friction leading to a value on a labor market state. If you didn't have the friction, if you didn't have the impediment to finding a job immediately as an unemployed person, or as a worker, as a firm offering a job, immediately finding a worker, if you didn't have those frictions, the model would not have any value at all. Okay, and once you have that friction, having the bird in the hand is worth something. It's worth more than two in the bush. Okay, so the valuation of having a job suddenly loses the immediate arbitrage of knowing about another job somewhere else. And this model, all the jobs are the same because all the agents are the same. So it's really focusing on a certain aspect. And in Morton and Pisker, we'll see that that wages can be different across jobs. Okay? And that's already complicated. But right now in the Pisker model, everyone's the same. In the bathtub, you're hooking up with people who are looking for workers, and if you're hooked up, you have a given productivity which is given by the model. So it makes things very simple. And already you get the insight that having a job is an asset. Losing it involves a capital loss. Who said that? Robert Lucas, right? Being unemployed is an asset because it means you have not just the benefit in hand, but you have a possibility of getting a job in the next period. Okay, that's the key insight. So to get into that, we're going to take you through these valuation equations. I'm going to take you into remind you of how the model decides on the wage, because the wage is a free variable. Once you've met up with a person who wants to hire you, you have to somehow settle on how much that person gets. And it's a free parameter in this model. So you could say the wage is given by a minimum wage law. You could say it's given by a union who dictates wages. It could be given by an employer who dictates wages. There are many different mechanisms. The one that Pisker chooses is Nash bargaining. So there's a fallback position for the worker and there's a fallback position for the firm. If they don't reach agreement, they can take these fallback positions, and the outcome is a sharing of the surplus that uses the wage as the sharing mechanism. So it's really simple. Okay? So here's the valuation equations. This is a discrete time model. Keep that in mind. We will launch into the Morton and Pisker model, which is a continuous time model. Okay, it's not a real big jump to make that to make if you understand what's going on. So here, implicitly, there's a discrete period. The wages are paid at the end of the period. The benefit is paid at the end of the period. The firm's profits are realized at the end of the period, and you discount using the interest rate R. And it's a financial system that is frictionless. Okay, so you use this discount rate to value these assets implicitly. And they're defined, these assets, we use the capital letter convention. I'll use the same convention when I talk about the Morton and Pisker add-on, as you will, basically as these capital W, U, V, and J. So you have two agents, workers and firms. You have two possible states, so you've covered the space of possibilities. Right? Just to remind yourself, please stare at these equations for a second. Okay, so U prime is the future value of unemployment. With probability S, you lose your job. With probability 1 minus S, you don't. Okay, so you're not leaving the labor force in this model. This is a two-state model. Unemployed workers get B for sure, and they get a chance of getting a job at value W prime in the second in the next period. Okay, and these periods are regularized. There's no variable time between finding jobs or getting matches. Okay, so it's a very rigid way to start the ball rolling. Firms, the firms get the rest of the surplus after they've paid the worker's wage. The same idea is used in the Morton and Pisker setup. And again, the firms have an option. They have a probability of losing the worker with probability S, the same probability the worker faces when the worker's employed, and 1 minus S is the probability of maintaining production in the next period. Any questions about that? So it's really basic, and I know you've seen it. It will get complicated in a second. Okay, so wages are determined by Nash bargaining over the current wage, knowing well that the value of employment in the next period is out of control of the worker. The worker can't influence that surplus. In the end, in a steady state, capital W equals capital W prime, and then the wage can be simplified considerably, but this is the problem faced by the worker. And the wage and the firm in this joint maximization of problem, and the wage basically maximizes this geometric product of the worker's surplus W minus U and J minus V from the firm's perspective. Okay, and the first order condition is simply a sharing rule. Okay, so the Nash problem gives us a nice sharing rule. The weights in the modified Nash bargain will correspond to the share of surplus, or the corresponds to both parties, and you can rewrite that, and then you basically have to make a few extra steps before we can get to an actual wage equation, but the step was involving a free entry condition for vacancies, and then imposing that those expressions that we had for the wage are in steady state. Okay, so we get this wage equation, and it's nice because it's all in terms of current values of the model's endogenous variables. And there's only one other endogenous variable. There's the wage, and then there's this theta. Okay, and theta is the ratio of vacancies to unemployment. So if you want, you can consider those independently, but in this particular relationship, the ratio of vacancies in the labor market to unemployment is the measure of tightness, and that will be a contributing factor to the wage. Everything else is parametric in that equation. Right? So we write the model down, we say workers have bargaining power summarized in a Nash bargain by beta. B is the income and unemployment. Okay, so that's fixed. And then there's beta, that's the workers' power. And then there's P, which is the productivity of the match, which is the same no matter who you match with. And then you've got this theta, that's the only endogenous variable. So labor market tightness in this simple model contributes to the wage. When V over U is high, the wage will be high. And when V over U is low, then wages will be commensurately lower. Okay, so that's that's in the Morton and Pisker version, there'll be more stuff that'll be added into this equation, but you should understand that labor market tightness, it's a very clear predictor. And you can run cross-sectional regressions of wages on local labor market conditions, and you can control for a lot of things, but that theta matters. Workers that have the benefit of being in a tight labor market will tend to earn more, all things given. Okay, that's a nice fact that you should remember from your labor course. Okay, so now we can take how we got there. I put this on the slide. You've seen this already. We can retrace our steps if we want. I think Thomas has done it ad infinitum. So it's probably nice to move to the comparative statics quickly. We want to think of two curves in this model, and I think Thomas showed you also that you can think of those three endogenous variables in a reduced way. You can actually just name them, the wage, and there's the rate of unemployment and the rate of vacancies. Okay, and it turns out that what I just said before is that the wage is really only a function of the ratio of those two. So in some sense, we're not really too interested in the wage at this particular point in time. You tell me theta, I can tell you what the wage is. That's kind of easy. Okay, and you can draw a curve if you want. But what's really interesting for us is this one. It's the relationship between vacancies and unemployment. Because these are data that you can grab for Germany across time, across Bundesländer. You can even look at Arbeitsamtsbezirke, local labor market districts, and compare these ratios. Because firms, usually have to tell you where their vacancy is being posted. So if it's to the extent that it's measured by the government, it'll be measured localized, and you'll have a number of people who are looking for jobs in that labor market. So you can literally plot these types of data in many different ways. Okay, we've done usually for a nation over time, maybe after taking out the trend, and we showed that last time. That's called the Beveridge curve, but that's just an empirical relationship. Okay, now maybe Pisker may have called the UV curve a Beveridge curve on some page of his book, but believe me, the spirit of the model is that the Beveridge curve is what we can observe in the data, and what you observe in the data is not one of these curves, it's the intersection of the two curves. The intersection of the VS and the UV curve is the point that the model predicts we observe in the data at any particular point in time, or in any particular local labor market, or both. Okay, that's an important thing to remember. Okay, does everybody get that? I mean, it's, and the reason why is because, economics gives us the freedom in our heads to do these mental experiments. So when one of these parameters of our model changes, maybe one curve will shift, maybe both curves will shift, and they may shift in different ways, and we should think really hard about what that implies for the points that we observe. And that's why, if you remember last time, I showed you a picture of US vacancies and unemployment after you'd taken the trend out, and then you kind of extrapolate what happened after the Great Recession, you saw that curve kind of changed. And what I was trying to convey to you is that most of the action in the United States seems to be a VS curve moving back and forth across a fairly stable UV curve. Okay, but what we observed in the Great Recession was suddenly a lot of Americans were unemployed and were not somehow getting back into jobs very quickly. And the Pisker model said it's because of something that the UV curve must have done. Either the S parameter changed, or maybe that X function, what Thomas calls the M function, may have shifted. So again, it's a question in econometrics of identification. And if you know something about econometrics, if you just look at a price and a quantity, you never know whether it's changing because the quantity, because the demand or the supply is changing, and that's what we have to get more information to identify that change. Yes, you had a question.
So because you said you can also apply to local
labor markets.
Can I assume that someone in the German Arbeitsagentur is sitting somewhere probably right now having more or less this picture and being like, okay, in Berlin we have this and this VS curve. So is it actually, it's used that way?
Believe it or not, yes. These data are gathered, and you can actually get them on the website right now. I would even go further because of the Hartz reforms. Every Arbeitsagentur knows about the local labor market conditions all over Germany, and I think is actually supposed to inform the unemployed searchers that there are job opportunities. If a young person just got his Gesellenbrief or whatever and doesn't have any work in Aurich, maybe they'll say, hey, maybe if you're willing to commute to Oldenburg, maybe you can find a job there. Sometimes they say, hey, if you really want, we'll give you some money and you can move to Bavaria. Okay, this is actually part of active labor market policy. But I'm not going to talk about that. I mean, again, this is a theoretical model. I'm just saying if you want, you could actually try to put the Pisker lens on any one of these local labor markets or all of them at the same time. You could probably learn something, okay? Because most of the action does seem to show a negative correlation, without any causation implied, between unemployment rates and vacancy rates. On the other hand, as I showed you before, if you live in a country like Spain where there's a lot of turbulence in the labor market, a lot of separations because of agriculture, because of tourism, then you would expect to have a different UV curve than you would have in, say, Hamburg or in London. Okay, so just keep your thinking caps on when you think about that, because it's important. Again, a model doesn't tell. Model is kind of a way of structuring your way of thinking about this, and the more fancy the model gets, the more we can actually put the data to the model and try to test the model. Okay. All right. So we have these two very strong statements. The UV curve. There it is. Now Thomas may have derived it with a symbol F for the matching function. That's perfectly fine. Again, I'm using an old paper that used a different symbol, doesn't matter. And then the VS curve is this simple applying the zero profit condition and equilibrium conditions on the valuations of the states and plugging in the wage equation that we derived already. Okay? So if you look at the second equation carefully, you notice that U and V don't appear. They only appear as a ratio, V divided by U, and that's theta. Okay, so this curve is easy to think about. It's just basically about the angle of a ray that emanates from the origin. Okay, so a lot of the things we'll be playing around with in a second are basically a matter of, it's just about changing the angle of that ray from the origin. Okay, so if you go back and take a look at that curve again, there are two things going on. One is the position of the UV curve, and given that position, what's going on with the VS. Okay, so let's take ourselves through that. Again, this is a repetition just to remind you, this is kind of important. One of the reasons this is a master's course is because we use math. And one of the reasons we use math is not because we like math, but it helps us be really precise, because there's no, why is the UV curve negatively sloped? I can tell a story, maybe the story is right. I can tell a mathematical story which is more precise. In fact, it may not be always right. It may depend on, like that, this Q function. It may depend on the properties of the matching function. So the reason we know the UV curve is unambiguously negatively sloped is because we've imposed constant returns on the matching function. That's kind of a good way of, as soon as you relax that, you might have a UV curve that has funny shapes. I mean, maybe if there's a lot of unemployment, maybe there's a scale effect and maybe matching will deteriorate more. We need to write down that function. So if you give me the minimum assumptions on constant returns to matching, I'm able to do, this exercise I did last time, which is simply a derivative, organizing a derivative of the implicit function v as a function of u, and then solving for dv du. Okay, so that's fairly easy, right? And if you can do that, then you can show unambiguously, given what we've written down, and we wrote down the initial assumptions when we started the course, that thing has to be negative. Okay, the slope is a different question. Okay, we need to know what s is. S is a constant in this model. So S can be high, it can be low, and we also need to know how efficient matching is. I just wrote down X. I didn't have any sort of shifting parameters because we know, because of the Hartz reforms, matching can become more efficient. It can also become less efficient for various reasons, etc. Okay. So let me take you through the shifters. I mean, it's not enough to know the slope of the curve, we also have to know what shifts it. Okay, so the UV curve is nice because it's simple. The VS curve has lots of stuff in there, and we'll do that in a second. But the exercise that I take you through very quickly would be simply asking the logical question, what happens if S changes? And then I'm going to augment X by adding a multiplicative term A, which basically is a way of making matching more effective for any given level of vacancies and unemployment. So a higher A would be like the Hartz reforms that say, okay, worker, you're unemployed, you have to show me every week that you've been looking for a job. Or I'm going to give you some job offers. Okay, I'm going to do what you said. I'm going to show you that there's a job offering in Oldenburg, and you have to go check it out. Okay, and the presumption is in this model, if I just put the people in contact, it will lead with some probability of success. In fact, the probability is 1 in this model. Okay, later on it might get considerably less than 1. Okay, so the way you prove this would be to rewrite the model, adding this multiplicative term, and then take the derivative holding v constant of u with respect to a. Okay, that would be like asking, to what extent does the curve get shifted to the right or the left? Or you can hold u constant and ask, what is the derivative with respect to a of v? Does v raise or lower vacancies, ceteris paribus? Okay, now what I do when I was raised to use calculus was to do the following, which is kind of an alternative to what we did before, which is just to take a total differential and then just set those things equal to 0 that we don't want to talk about. Okay, so the thought experiment is I change A, what happens to U given V? Okay, so if you take a total differential, you get this expression, and then you just basically choose what am I interested in? What are the derivatives that interest me? Okay, and again, this is all about holding everything else constant, letting A change, and ask whether the UV curve shifts outward to the right or inward to the left. And I've already told you kind of the answer, but you should be convinced that this is the right answer, okay? So let's look at ds. The change in this particular case would be changing the rate of match dissolution. So remember, you have the inflows into unemployment, which is S times the stock of employment, and then you have the outflow rate, which is the unemployment stock times the matching probability coming from the matching function. Okay, and then you could do the same exercise holding u constant and solve for dv dA, okay, which is what I said before in reverse order. So this is like shifting the UV curve upwards. Downwards or inwards. Okay, so an increase in matching efficiency is like moving the UV curve inward. Okay, so again, I did this early just to, or first just to make it easy. And I have a diagram I'm going to show you in a second, which just shows you the direction of those shifts. So S goes up means the matching becomes the matching efficiency is the same, but there's more to match because there's more inflows into unemployment. So the UV curve is going to lie up above and to the right. And if A goes up, if A rises, then the matching efficiency has increased and the UV curve shifts down or inwards. So that's the comparative statics tricks that we'll do. And you can use this, and we will use this. The general principle is we can use this to think about all the different types of parametric changes in this model that you care to think about. And the procedure is the same. Take the model. It may be very nonlinear. When we use calculus, we're actually asking for a very, very small, we're asking about the small infinitesimal effect of an infinitesimal change in one of the things that we take as given. So it's always important when you do this kind of analysis that you remember this is not necessarily true in quantitative terms for large changes because things may be non-linear. Okay, so keep in mind this general procedure as we move through. I was just trying to give you the example. Again, you can do this for the VS curve as well. And I told you already that the VS curve can be thought of as a ray, an open ray from the origin, excluding the origin. All those points only matter in terms of their ratio. So whatever comparative statics experiments we're going to take through, they will basically change that implicit angle that VS makes with the horizontal axis. Okay, and if you remember from last time, I alluded to this. It's easy to use the methods I just talked about, comparative statics, to show formally that an increase in the productivity of the match, again, this is an unconditional constant in the model, raises the value of the surplus once a match is formed. Given the bargaining power of the workers, that means that there's going to be more for both. So you'd expect the VS curve to lie above the VS curve previously. Firms will be willing to post more vacancies because it's more attractive, and the value of vacancies will have risen above zero. And similarly, if productivity falls, the VS curve rotates clockwise to a position below the previous one. A change in the benefit level, income and unemployment, has exactly the opposite effect. So a rise in the benefit makes workers get a bigger piece of the surplus. Everything else given would mean that vacancies are less attractive to post, and the VS curve would shift downward. You cut the benefit, workers have less bargaining power. The capitalists, the firms posting the vacancies, see profit in the vacancies. They post more vacancies. The number of vacancies rises. The curve shifts in a counterclockwise direction. And you can tell the same story with worker bargaining power. C is the cost of posting a vacancy. Okay, so that also matters from the firm's perspective. And you can see that the Pisker model really makes clear that because of the friction, every match is a power struggle between workers and firms that are in the match. Okay, so it has a certain flavor that's non-neoclassical. You don't have to say what kind of non-neoclassical. It certainly has the friction means that bargaining is going to be important, and the rest follows from the things we've spoken of already. Okay, so keep that in mind. Here's the diagrammatic representation of, just to remind you that the intersection is what matters. Okay, so we started at the green point to the right, and VS and UV intersect, and suddenly we have an increase in matching efficiency. We have two things going on at the same time. One is we have a shift downward of the UV curve, and we also have a counterclockwise rotation of the VS curve. Okay, this is because in some sense matching has become more efficient and makes it more attractive to post vacancies. Okay, at the same time, an increase in the separation rate. Again, you have to tell a story as to why this would happen. Maybe the economy moves to more sectors where there's more fluctuation of employment because of the nature of the beast, because of agriculture or certain types of industries, or possibly even tourism, seasonal tourism and the like. that would cause the parameter S to rise, and that would cause both a shift in the UV curve as well as a shift in the VS curve. Okay, and as you can see, there's an ambiguity in the outcome, which is the vacancy rate. It's not possible to say whether the vacancy rate rises or falls without knowing more about the parametric values of the model itself, because it's a qualitatively ambiguous derivative. Okay, in contrast, the effect for employment is unambiguous, just as the effect for unemployment is unambiguous in the case of matching efficiency. Okay, this is why the model doesn't always tell you all the answers. You need to know more. I mean, some of these shifts might be quite small, modest, and in some cases they might be quite large. Okay, so be careful. Be careful of the ambiguous versus unambiguous outcomes. So you can see we've already got a lot of tools under the belt, so to speak, to think about things like this. This is where neoclassical sort of basic supply-demand analysis that we learned in our labor course kind of falls short. A lot of the effects that Pissarides identifies are not even evident in a simple Marshall supply-demand framework. Okay, so the unemployment benefits have, you can always say, okay, it increases the worker's bargaining power with the firm, but it also affects the workers' incentives to stay in unemployment, or affects the valuation of unemployment. This is something that Pissarides has given us some insights into. We also learned the bargaining power of the worker is important. The bargaining power of the firm as the complement is important. Things we've never talked about before in labor economics. What does it cost to post a vacancy? Suddenly becomes important. Okay, so search costs from the firm's perspective are important. The separation rate. Okay, matching efficiency. So all these things matter, and you can actually even using the limited Pissarides framework, you can even add more things. So when I was one of my first papers I wrote on my own was adding job separation costs to the Pissarides model. So the Pissarides model had just come out, and the question was, what would happen if I put a tax, if you will, basically, if you put a tax on the transition, going back to my original valuation equations, imagine paying a tax if you're a firm, if you lose a worker. Okay, suppose if you go from the state employing a worker with value J to losing the work with value V, for that transition you had to pay an extra severance cost, call it F. Okay, and make it exogenous, just to make it like you have to pay a lawyer. And the worker doesn't have to pay the lawyer. But of course, in the model, the worker will have to realize that the firm may have to pay the lawyer in the future, and therefore that F does show up in the end in the Nash bargain. Okay, so it has an interesting effect on the model. So you could take this Pissarides model as easy as it is, and you can already extract a few interesting insights, but it's not enough. Okay, so that's why we as critical economists should stand up and complain when certain things don't seem to be smelling right. So I'm going to ask you to make this a completely participatory exercise. I've already told you what the strengths of the Pissarides model are. Okay, we have an explicit role for vacancies, not evident in the Marshall framework. We have explicit frictions. We're not necessarily saying that we have directed search or complicated search. We'll talk about that later. We also have this interesting insight of asset valuations. Okay, so we can explain why workers are unhappy when they lose their jobs. It's already quite an achievement, because in the simple Marshall paradigm, workers should be indifferent at the margin between working and not working, right? Because they can always get a job at the going wage. And that's just not what we think the world looks like. So the insight of the Pissarides model is very strong. And I'm not sure if you, Thomas, got to this to talk about Shimer. Okay, but let me just tell you one more thing. Another thing that we notice in the data, and this is worth thinking about, which is in the data, and this is true of every country that gathers these data, the ratio of V to U is extremely volatile. It moves a lot. Okay, so in good times, In good times, vacancies go up a lot relative to trend, and unemployment goes down a lot relative to trend. That ratio moves a lot. And it moves a lot compared to most other things we observe in macro, in the data. And Robert Shimer in the 2000 decade wrote several influential papers saying that these movements are not even consistent with the Pissarides model. But at least the Pissarides model writes them down. Okay, so go back to the UV curve. Now, let's do this one. I should be able to jump back and forth quickly, but I don't. Okay, so if I'm telling you that the UV ratio, the VU ratio, the vacancy ratio moves a lot, what curve is moving most in this picture, do you think? If I told you they're moving in opposite directions and they're moving a lot, what curve has to be moving? The VS curve. I mean, there's only two answers, right? So, I mean, think about it. The VS curve moves in a clockwise direction or in a counterclockwise direction, counterclockwise, clockwise. From my perspective, that means that along a UV curve, we're going to have sharp movements of the ratio V over U. If the UV curve is moving, that would tend to dampen the ratio's movements. Okay, so this means that the things that Pissarides talks about in the VS curve must be moving over the cycle if the model has any content. Okay, so what are the things that could be moving over the cycle, the business cycle?
The bargaining power?
Possibly. Okay, the evidence is mixed on that, but it could be. Okay, beta could be cyclical. Keep going, try something else.
Benefit and gets at least after.
Okay, but that would imply that in booms they cut the benefit. Probably not what we would. Yeah?
Interest rates?
Possibly. I mean, these are all possible, right? You can have to trace through the. But again, interest rate going up would actually make the curve flatter, if you think about it. So that's not kind of what we want. In spite of higher interest rates, the curve probably moves in the other direction in a boom. But what really moves in a boom? We know this, and this is what saves the Pissarides model. It's productivity, P. P is extremely procyclical. Okay, so productivity goes up in booms. In most countries, it goes up in booms a lot and goes down in recessions. So Shimer basically took a model like this and put a macro frame on it and tried to see how well the model could predict this high volatility of V divided by U. And he found that it doesn't do such a great job. Even though it gets the direction right, the magnitudes are much larger in the data. So that's called the Shimer puzzle. So you could praise the Pissarides model for giving rise to the Shimer puzzle and giving us a framework to think about it. Okay, and I'm really glad that you're not taping this. So we got as far as here, okay? And again, the hints on how to explain the Shimer puzzle are even more interesting than that. You could also say, maybe wages aren't Nash bargained. Maybe wages are rigid. Okay, so the guys who basically solved the Shimer puzzle, Shimer, Hall, and some other people, they say, if we make the wages kind of, if we put features of the model that make workers and firms negotiate kind of rigid wages, that does great wonders. Because in booms, productivity is rising, the workers don't get any of the surplus, so they get very little of the surplus, and the firms say, hey, let's post some vacancies, and then vacancies explode. So that's the way you get the model to work, okay? And there's a lot of debate on this still. It's an open topic for research if you're interested. It's a great master's thesis subject, the Shimer puzzle, okay? Robert Shimer, AER 2005. So I wanted to ask you what you think the weaknesses of the Pissarides. This is the lead-in to the Mortons and Pissarides. Okay, so who wants to give it a shot? If you were like a critical economist, put your critical hat on and just be nasty. Anybody? Yeah.
It assumes some kind of bargaining between the worker and the firm, which may be a violation because some, I don't know, they can have the whole bargaining power.
Well, you could say that workers have very little power. So you could take a real sort of,
That's also included in the model.
but you can still set beta close to 0, and that still kind of, and that would do exactly that's the way a lot of people attack the Shimer puzzle. They say workers have very little power, so the bargaining set's very small, and that gives us kind of rigid wages for endogenous reasons. Okay, but that's not what I'm looking for. I'm looking for a criticism of the model's assumptions that kind of tie our hands. So, I mean, what's the most obvious thing that's kind of wrong with the Pisker model? And everyone's the same. Everyone is the same. And believe me, that is the hardest thing to do in economics, is to make everyone not the same. I mean, it's the whole idea of heterogeneous agent modeling in macroeconomics is incredibly difficult, because once you allow people to be different and you allow them to save and accumulate assets, then they become different in ways that are kind of means you have to keep track of them. We've got a representative type of agent here, a representative firm, a representative unemployed person, a representative employed person. And this is kind of a first attempt to make something heterogeneous in this framework, right? So what do we make heterogeneous? Lots of things you can make heterogeneous. You can make match productivity heterogeneous. So that's what Pisker and Morton did together in the next level. Is to make, we come together and then something happens, and then after that we're like getting married, and things can get better or worse, and at some point if things get really bad, we call it quits. So you're already getting the idea. Matching in labor markets is like getting married. It really is. Okay, and don't forget that. It's really important. Okay, and similarly, extending the marriage metaphor, what else would you think about? And getting married is about getting married, and?
Maybe some couples are more likely to be separated.
Very good. Okay, so we've assumed S is constant, and that is just very convenient, but it's a modeling trick. And in fact, we want to allow for heterogeneity in the conditions that lead matches to separate. Okay, we're going to take a very small step in that direction. We're just going to assume that the separation rate is no longer exogenous. Okay, we're going to make it endogenous in a special way. We're not going to go all the full Monty and allow every couple to be separate, totally independently idiosyncratic about their preferences of staying together, but you could push this much farther than we do, and they did in their. It's just already a step in the right direction. Okay, so the Morton and Pisker model is an attempt to solve those questions. That's kind of the way I'm going to sell it for the next 45 minutes, and next week we'll go into more detail. Thomas will take you through the stripped down version. So Thomas will take this model and set a lot of things equal to 0, so you'll go back to almost a post-Pisker type of setup. But I'm going to give you what I think is a really nice summary of the paper that was presented by them and was published, I think, in the Journal of, or in the Handbook of Labor Economics on policy analysis using the MP model. So I'm going to give you all the different things. I'm going to get you excited about it, and then we're going to go back and do the bare bones stuff. So what does this model do? It allows for the Pisker model, positive stuff. It allows for job openings, we call them vacancies. It allows for workers that are looking. We have ex ante identical workers still. So we're not going to go as far as we could by saying that workers unemployed also are heterogeneous. Workers are homogeneous when they're unemployed. And that, again, makes it easier for us as students and and analysts to understand this model, and later on we can make it much more complicated if we want. Most importantly, we have a match, and once the match is made, there is heterogeneity in a way that we can describe using what's called a Poisson process. Okay, a statistical process that evolves over time in a special way that the probability of an event depends on the interval of time between changes. Okay, so I'll deepen that idea in a second. That makes it necessary to have a continuous time setup, so we'll discuss that. The Poisson idea is a very important idea in labor economics. Okay, so again, we're moving through time. You're looking for a job and you have a certain probability of finding a job. If that probability is describing one of two states, finding a job, not finding a job, then you can make the interval of time that we're talking about really small, and you can think about basically times between incidences of this event. Meeting a worker, for example, worker meeting a job. So we're going to push that margin a little bit in this setup. So we have heterogeneity of job matches. So I'm going to go back and describe the 94 aspects before we present the 99, the model. They're all very similar. I'm also going to use, instead of X, I'm going to use M like Thomas did in his lecture for the matching function. So X now has a different meaning. X is the productivity of a worker in a job match with the firm. Okay, so again, we speak of firm productivity with the worker productivity with the firm. We're really talking about match productivity. Okay, so I'm going to use that possibly a little bit loosely, but a match has a productivity, and we're going to call it X. X is drawn from the unit interval between 0 and 1. Okay? Now, Pissarides and Mortensen in their initial paper were very clever because they wanted to shut down the following. They wanted to shut down a lousy match at the beginning. Okay, so it's like when you get married, the beginning is just awesome. Right? And after that, it can only kind of go downhill. Because you learn more about the other person, etc. It may not go downhill by much, but in some sense, it's the best. Okay, so that's what they assume. So when you get married, X equals 1. And because they assume that, there is no rejection. Okay, remember in Pissarides there's no rejection. And in Morton's and Pissarides in this version, there's no rejection because at the beginning, X equals 1. And then after that, we have Poisson arrivals of a new draw of productivity. Okay, so I'm going to detail this with excruciating detail in a second. But just remember, you meet, X equals 1, and then after that, you're subject to a Poisson process. Your match productivity is a Poisson process with an incidence probability of lambda. Okay, so lambda, you think about this as the probability between t and dt plus t of some event happening. Okay, so either the event happens, you have a shock, or you don't. And if you don't notice anything. Nothing's happened. If something happens, then, wow, I learned she has bad breath, or he has bad breath. Okay? I can handle it, but that changes my information set, it changes my decision problem. Okay? So if the shock occurs, conditional on occurring, the value of X is drawn from a distribution with a CDF of capital F. Okay, so this is, again, it's a cumulative distribution of this X, and it's time independent, so it doesn't matter whether the good times are bad. I'm gonna, with some probability, I'm gonna have this incidence, and once I have the incidence, then I get a new draw of X. So X starts at 1, and then it becomes something else. It could also be 1 again. That's a very low probability event. It's probably going to be lower. It might be a lot lower. And then I'll be waiting again for the next Poisson incidence when I pull another value of X. Okay, so it's X equals 1, goes to some other value, and then it may go up again. Maybe things are great. We both like to collect stamps. We like the opera. Wow! And then eventually, the problem is, at some point, you might have a really bad day. I mean, you might have a bad realization of X, and you say, okay, this is really bad. I think I can do better. And then you and your partner agree to dissolve the match. That's the Mortensen-Pissarides model. This is the way I'm going to teach you what a reservation property is. Reservation property of a model means that I behave optimally when I choose a value, a minimum acceptable value of productivity in this match, and if I have the Poisson draw and x is below that critical value, then we dissolve. It's a mutually agreed separation. So you and your partners say, it was nice knowing you, but I think we've kind of reached rock bottom now. We're gonna separate and go back into the market. So to make sure that you understand, there is endogenous separation in this model, but it's mutually agreed. Both employer and employee had the same information, and they say, it was nice, let's call it a day. Okay? So, this may not appeal to all of your preconceptions about how workers and firms go separate ways, but in fact, if you look very closely at the data, a lot of times firms kind of tell their workers, things aren't going well, and not just we have a bad business cycle, but if we do have a bad business cycle event, you're probably not going to survive. It's kind of this implicit communication. So the worker may see that coming, or the worker may see it coming that the job is coming to an end and may leave. So all these things kind of proxy. This model is assuming that workers and firms basically say, yeah, I'm too old. You've got a better production possibility with some other guy, etc. Okay, again, it's a restriction because we're going to use Nash bargaining to get to that endogenous separation reservation value. You could assume that the wage was rigid. You could do all sorts of other things to get involuntary separations, but we're going to stick with the MP setup just to train you to think that way, and then later we can do something else. Okay? Yes, question?
And so the productivities of the match X are heterogeneous, but this Poisson probability lambda
is constant.
So say when we match up and we get different, like you said, different productivities in different periods.
Yeah, it's mutual. You and you're my boss. I work for you, and our productivity evolves as I've described it.
Yeah.
Okay, and we both face the same lambda. Lambda is universal for the entire economy.
Okay, so then if we split up and the boss had to get another worker, if they would face the same lambda again.
Yeah, but they start at 1.
Again, okay.
See?
So okay.
Yeah. So we can derive all this later because we'll write down the valuation equation just like the easy Pissarides model. The more complicated Mortensen-Pissarides has the same idea, but you got to. Everyone's thinking ahead. Like you said, if we split up, I got to find somebody else. It's going to cost me something, but it might be a dream match. And by construction, this model, it's always going to be x equals 1. And so Ramey and other people have worked on models where you can actually allow for initial productivities less than 1. But it doesn't add a whole lot. It makes it a lot more complicated to work with, okay? You have a question? Anybody else? Other questions? Okay. So the separation rate now is the probability of an incidence, okay, in this very short interval of time. Again, we're in a continuous time world, so between t and t plus dt, something can happen. Either we have an incidence, okay, so I suddenly get shocked, and then given the shock, I have to find out what x is. I put my hand in the urn and pull out a new value of x. Those things are joint. So the probability of actually separating from my job is the product of this Poisson incidence parameter and the probability that my x is below r. R is the cutoff value, which will be determined in the model. Right now, it's just for whatever value of r you want to call out, that's the probability. So you can see that we already have a great angle on making S endogenous. S is, in this model, will no longer be endogenous. Will no longer be exogenous, it will be endogenous. Right? Now, think about what does that mean? The higher R, does that mean my separation rate is higher or lower? Well, remember, F is the cumulative distribution function, so F is increasing in R. So higher R means higher probability that I'm underneath, which means I'm probably going to get separated. I'm going to get separated. So the separation rate is increasing in capital R. Think of capital R as the threshold. So the closer the threshold is to 1, the more likely it is that if I do have bad luck and have this incidence of the Poisson process, I'm going to separate. Okay? So think of R as a measure of fragility of the match. The threshold value, if it's really low, if it's close to 0, that means that, I can do whatever I want. My job, I'm so productive, my boss loves me so much, we're not going to separate. Okay? But if R is high, if R is close to 1, that means that any incidence of a shock will probably lead to a separation. Okay, so R is going to be one of the key endogenous variables of the MP model. Keep that in mind. And we call it a reservation productivity level. That's why it's got the symbol R. So, and it's a great indicator of fragility of the match. So the higher R is, the more fragile any given match would be, because the workers have the same, everything else is the same. They just have they have the same incidence parameter, they have the same draw, the probability distribution of the draw of the new productivity is the same across workers. So, now you can already see some drawbacks of this model. The history doesn't matter. Okay, so again, why doesn't the history matter? Well, the first answer is it's really complicated to track for every worker the history of that particular worker. So if you thought history mattered, then it would be a very difficult, computationally challenging problem to solve. That doesn't mean you shouldn't do it. But in terms of us understanding the mechanism, probably wouldn't help us very much to do that right now. So the model is basically treating workers in the match in a sort of a very special way. It's trying to capture a few aspects, but it can't capture everything. So if you believe in human capital, if you think human capital matters, then you would think that over time your human capital makes you more and more valuable to the firm, and that would lower it would raise your productivity and also lower the threshold of a new probability that would make the firm interested in getting rid of you or you getting interested in leaving the firm. So the model is open to that, but it's just hard to track. Okay, so again, you're willing to invest a lot of computational time in tracking heterogeneous agents with heterogeneous human capital stocks over time, then you're welcome to do that. But right now we'll keep it simple. And now I'm going to try to modify this to give you the flavor of this policy-oriented version. So I'm going very slowly and I'll spill into the next lecture because it's really worth, and Thomas will talk about it too. It's interesting to think about this MP model in some detail. And a lot of people call the model now the MP model, even though you might say it's actually more Pissarides style, putting matching in macroeconomic models. But we're going to spend some time thinking about this. The value of the MP model is because you can add all these different policy bells and whistles. And one of the things you can do is actually make workers have different skill levels. You can actually define separate labor skills, and you can define separate labor markets by skill. Okay, so you can take the same model and just call S productivity in the skill class S and have that define a labor market which operates separately from the other labor markets. And again, remember, if you're a firm, you basically can employ a worker, or you can't employ 3 or 4 workers because you have constant returns to scale. It doesn't matter from our perspective, but you might think that's a problem. Not the end of the story. Okay, so the model also allows for a lot of distortions. So what I'm going to show you now is to show you that what we had before with Pissarides was very simple. You had a vacancy posting cost, you had a productivity of the worker in work, you had a benefit of the worker could draw if the worker were unemployed. We can do much better than that. We can even think about labor market policies. I already talked about training, job subsidies. In France, for example, if you work at the minimum wage, the government may pay for your Social Security contributions. There are all sorts of things you can think about that are hard to think about in a classical labor market setup. So what kind of interventions am I talking about? I mean, I obviously talked about unemployment insurance already. we talked just about subsidies, but you can also talk about labor taxes. So you can put those in. I mentioned already that you can put a severance restriction or cost of firing a worker, cost of a match going, of match participants going their separate ways. You can think of active labor market policies, and you can even think about apprenticeships in this model. So it's a really powerful setup that is usually not very easily adaptable, or it's not easy to adapt the Marshallian sort of the labor supply demand framework to think about those issues. Okay, so let's do this. We already talked about the matching function. The matching function looks like a production function. We're going to stick with the CRS assumption, constant returns to scale, and I'm going to use a little m to stand for that. I don't know if you use capital or small, but it doesn't matter. Okay, that's going to be the basis for this friction between workers that are looking for work and firms that are offering jobs. Okay, so we have the same notion of a contact probability. The sufficient statistic for this contact probability will be theta, will be the labor market tightness measure. You learned already last week that if I tell you what the contact probability for firms is, given the stock of vacancies, then you can derive using theta the contact probability for workers. Okay, so there's this very important relationship, F equals theta times Q. Q is equal to F divided by theta. Okay, and again, this is supposed to summarize the same thing we talked about before. Now, I don't know if Thomas told you about this, but and we will learn this in detail later, but I want you to convince yourselves that these parameters have lots of interesting information, and since everyone's the same, if the job finding rate is given by F, which is equal to theta times Q, then it's easy to show that the expected time you will be in unemployment is 1 over that rate. So it's 1 over F. Hi. You're on TV. So 1 over F is the expected duration. Now look carefully at that expression. That says that, unconditionally, without knowing anything else, and not knowing that you're, this model, the conditional duration, expected duration, conditional on spending end periods is the same, right? Nothing changes by being a long-term unemployed person. In reality, it might affect your exit probability. But in this particular case, it's easy to show, and we will show it formally in a couple of weeks, that the expected duration of unemployment is the inverse of the finding rate. Okay, and that's true either in continuous time or in discrete time. And correspondingly, the expected duration of the vacancy is the inverse of the vacancy posting success rate, or the vacancy success rate, which is equal to 1 over Q. Okay, so keep that in mind as we take you through the model. I told you already that match workers and with a job or a firm have the highest level of productivity, so X will equal to 1. Now, if you want to take this to allow for skills, you could say, okay, in the job market for skill S, it would be S times X. But S is exogenous; you can't change your skills. So it's just kind of to show you that you can actually augment X with some constant, just like we did in the Pisker model. So just think of X as being just a measure of productivity relative to the top. And if you're in the top skill level, X would equal 1. And the version that Thomas will talk about, and I'll talk about next time, is the stripped down Pisker model, S is equal to 1. Just a single labor market. But just to give you an idea that you can actually have separate parallel labor markets. X changes according to this Poisson process, parameter lambda, I told you already, and the shock is drawn from the CDF. Okay, and therefore reservation property holds. And this really holds because the model is cooked so that it holds. There are lots of different models we can think about, and we will talk about later, where the reservation property has to be proved, okay? But right now, the optimal behavior of the firm and the worker in a match will be that anytime we have a Poisson incidence and productivity falls below this R, which I put RS here because it's conditional on the skill. You can get rid of S later on, we will. So the duration of a match is the inverse of lambda times F. And you can think of lambda F as being exactly the parameter S in the Pisker model. Okay. So we also have the other stuff is very similar to Pisker. Okay, so we have a fixed mass of workers that can either be unemployed or in work, and if they're out of work, they're searching. So that you can't opt out in this model. If you're not searching, you're working. So it's employment is equal to 1 minus U. Okay, and the supply of vacancies, as in Pisker, is elastic. In fact, whenever the value of vacancy deviates from 0, the big V is not equal to 0, you will have firms entering if capital V is greater than 0, or firms exiting if capital V is less than 0. So the equilibrium no profit condition we're going to talk about is V equals 0. That's going to pin down the model, just like the Pisker model. So again, I guess the marriage of these two guys in this set of research they did was to basically show that this is a very powerful assumption, right? It's just a statement about firms looking for workers, because nothing happens until you get a worker. But you have to pay the cost of posting a vacancy. So it's the same idea as before. This equation is the differential equation that describes unemployment over time. It just says, as the very first lecture, unemployment evolves as a race between the inflows and the outflows. Inflows is the separation rate times the employment stock. Okay, remember this is normalized to 1, so think of this as the same thing as the employment rate, if you like, but it's really the stock of employment, the fraction of workers that are actually in job, multiplied by lambda times F, which is the separation rate. Lambda is the incidence parameter from the Poisson process. And F is the time invariant distribution conditional on the Poisson incidence. What is the value of my productivity? And R is this critical value, which we have yet to determine. The outflows out of unemployment is simply the finding rate for the workers, which we called F, times the stock of unemployment, which is U. Okay, so it's the same equation, except it's just a bit fancier. And the goal of our analysis from now on in will be to try to figure out how to endogenize R and endogenize theta. Okay, because in this model we can actually think all the time in terms of theta. We don't have to think about U or V. We can derive them, okay, but in fact, for graphical reasons or for analytic reasons, we're going to try to endogenize R and theta in the first instance. Everything else, including the wage, will flow from that. Okay? So again, this is just if you set du dt equals 0, there's the value of U. Unemployment is, again, this wonderful expression that we had before at the very beginning of the first lecture, S divided by S plus F. But now we've got this fancy we've breathed life into S. S is now equal to lambda times F, evaluated at the reservation productivity level. And F is given by the matching function, which is this is theta times this vacancy placement rate, which is also a function of theta. Okay? Again, you could write F of theta, but again, in the interest of efficiency, we know that if we know Q, we can derive what F is going to be given theta. Okay, so I'm going to give you, the rest of it's going to be verbal, and I'm going to write down the valuation equations. I just want to make sure that you understand this is a natural outgrowth, also in the intellectual history of economic theory. It was actually just an obvious next step from Piskerides' path-breaking work in the 1980s. Okay, so the idea of having this matching function, frictions, bathtub, and then heterogeneity of the match, and having a bit more endogeneity on the productivity of a match. Okay, so what is important to understanding what I just said? First, the match is allocated. You have match surplus. The real wage is the allocator. You don't have a marginal condition like you have in labor economics. Marginal product equals wage, or marginal rate of substitution equals wage. In the MP model, the wage is an allocator of surplus and nothing more. Okay, and remember, that's what makes this setup pretty special, because it kind of cuts the wage loose. It doesn't depend only on productivity. It doesn't only depend on, it depends on things like frictions in the labor market. It depends on the cost of posting vacancies and the rest. And this follows from wage determination being driven by a Nash setup. So the wage will split the difference. The wage is flexible in this model. It's perfectly flexible. Okay, so this is not a real rigid wage model. The wages, and that's why we talk about the mutually assured match destruction, means that the wage will always allocate whatever surplus is left in the match, and if things get really bad, the surplus of the match goes to zero. Right? At some point, we just say, let's call it quits. Okay, so in some sense, the wages, the workers will give back, will actually give back wages if they'll take wage cuts in this model if things get really bad, up to a certain point. That's, again, you might think that's unrealistic. We've seen that. We've seen it in the United States. We've seen it in Germany. But again, it's part of the model. If you want to have rigidities in there, you're going to have to put other aspects of the model to make it do that. But again, already it's kind of interesting. So what else can we want to put in the formula before we start writing them down? We're going to have B like before. Pisarides and Mortensen have a wage-dependent component. So in a lot of countries, unemployment benefits depend on the wage that you just got, or some average wage. So you could think of rho as being some replacement rate. Okay, so like in Germany, if you're unemployed, you usually get something like 60% of your last net wage, okay, for a certain number of months, 12 months, or if you're older, you get maybe 18 months. And there was a time when it was more, time was less. Okay, you can add, again, this model is so powerful, you can add things like a subsidy. So suppose the government wants to give just write a check. If you find an employer and you start working for her or him, you get a check, and it could make it even skill dependent. Okay, so you might want to have a skill dependent hiring subsidy. Maybe you want to help the low skilled workers or whatever. You can have hiring costs, so you can think of a one-off cost instead of a vacancy cost. Maybe there's a cost to training a worker. You maybe have to buy the worker some clothes, special equipment. Maybe they have to go through a course, and it's one time. It's non-recurring. Okay, that's what makes this model really powerful, because once you go into the marriage, you have to buy all the equipment. And then you may have some bad luck and you have to break up. Okay, then you have to get a lawyer or something. Okay, it's the same idea here. Okay, and you can even add on more layers of complexity. You can add a firing tax. I talked about this already in the Pisarides model. The cool thing about this is that the firing probability in the old model was constant. In the Pisarides model, it's not a firing. The match dissolution rate is actually endogenous. And it will actually depend on this firing tax. Okay, and you can have bargaining power, obviously, we have that already, we've had it before. You can also have a tax on employers. You can make workers and firms pay for Social Security contributions. Like in some countries, there's a flat contribution of the firm, call it A, or you might have a worker wage-dependent employer contribution, like in Germany. So you can add all these things, and of course you have a vacancy posting cost. So this is what the valuation equations look like under those conditions. So it looks a lot more complicated now, right? I'm just trying to give you a feeling for the complexity, the potential upper bound of the complexity of this model. And I'm going to take you through verbally. Don't get scared. Next week we'll do the simple strip down. We'll set a lot of this stuff to zero. And we'll go back to sort of the Pisarides mode for a second. Just, again, it's all about changing parameters and looking for comparative statics effects. In this complicated version, which is useful for policy, what do we have? We now have a continuous time model. So I'm going to look at on the left-hand side is the implicit income of owning asset J. So I'm an employer, I have a worker in place. In the next instant of time, I'm getting income from that. The opportunity cost of that asset would be R times J. So if the matched worker were worth cash to me, I put it in the bank, I would get R times that in the next dt. Okay, so the left-hand side is kind of like the value, the income value accruing from asset J. And you could have done the same thing in the Pisker model by rewriting it in a special way, but in a continuous time, this is like letting the interval of time shrink to 0. Okay, so during the period I've got a worker, what do I get? I get productivity, and if S is equal to 1, it's what we're going to do next week. S is some skill scaling factor. So that's my product of the firm worker match. I have to pay A to the government, and I have to pay taxes T times W to the government. I also have to pay the worker W. Note that I've made W a function of X. W is now productivity contingent. Okay, so it's suddenly really, now I'm working for this guy, and he's looking at me, and he's looking at what I'm producing, and if I become suddenly productive, I can actually expect to get compensated for that, because the Nash bargain is going to basically partition the surplus that we get out of our match. But given W, okay, the last time I get to set W will depend on what X was the last time it changed. Okay, so remember, X starts at 1, and then it kind of changes over time, and at some point it will probably fall underneath this reservation, and then we break up. Okay, so that's the revenue side minus direct costs, and now we've got the next part, which is very interesting. So we've got, in the next instant of time, I can have an incidence. Okay, so remember, lambda is the probability that something happens to X. Okay, now, so what happens to X? X can either be great, which means that it's better than R, or it falls below R, which means time to break up. So let's do time to break up first. That's the easy one. That's the last term. Okay, with probability lambda, I get the hit with the Poisson incidence, and then with probability F of R, we break up. Okay, so the product of those is the probability that we break up in the next instant. And if we break up, what happens? I have to go back into the vacancy posting mode, and I have a capital loss. I lose J of the last value of X, and I also have to pay the severance tax. I got to pay the government or a lawyer or somebody because of this, again, the red tape costs of the job separation. Now, in the model that we'll do next week, we'll strip this down considerably. We'll get rid of all these bells and whistles, but we'll still have J of X, because the firm has to, if the firm continues to exist, it's going to have J of X, and if it goes onto a vacancy posting mode, it's going to get V. So that's the bare bones, the Pisker logic, if you like, from the previous lecture. Okay, now the term before that is a bit more complicated, but it kind of has the same flavor. Okay, this is good. A good thing happens to me. I get the shock, and the new value of X is actually above what it was before. Okay, and what it was before was X. So I'm going to take all the values of X that are greater than, I'm going to take all the values that are acceptable to me, lying between R and 1, and that's what that integral stands for, and I'm going to take that value, that expected value of that. So with integrating over the density of the realization of X is going to be df, capital F, which is shorthand for little f of X dx, or f of z dz. Okay, so that second term, that integral is supposed to be the expected value of continuing with this worker at a new value of X that I don't know. I just know that I've drawn one that's favorable to me. It's above R. Okay, so that's the threesome in the Pisker world. Nothing can happen. Okay, so there's no Poisson incidence in the next period, so nothing happens. I'm still at J of X. Or something happens, and it's a good thing. Okay, and the good thing would be that I get I'm still alive. X is, in the new draw, is above R, and it has to be less than 1. And then, of course, I might have bad luck, or our match might have bad luck, and I draw an X that's less than R. Okay? So that kind of describes the asset valuation of having a worker in work. That's a kind of hard one to swallow. We'll go over it in the end. We have to also derive a lot of stuff, but I wanted to just give you a flavor of the logic of MP before we go into the details. So if I'm working, maybe the logic would be for me to go to the firm not having a worker in hand. So we'll skip to the third equation. That describes the implied asset value of a vacancy poster. So I've posted a vacancy, I don't have a worker, I'm out there in the bathtub swimming around. What can happen? First I have to pay K. And I'm scaling K by S because it's the skill factor, okay? So in the skill market, S times K is my assumed vacancy posting cost. So I have to pay that regardless. And if I have bad luck, with probability 1 minus Q, I don't get anywhere, okay? So I still have, what I do have is basically the probability of getting a job match, which would give me J sub 0. That's the initial value of a successfully posted vacancy that's matched, minus V, which is what I have if if nothing happened. And then I may have to pay some costs. So C was the cost of hiring the worker, and H was the subsidy I might be getting from the government of hiring the worker. Okay, so that's a prospective capital gain, if you like, from moving from a vacancy posting state into a state we call J, okay, the state of having value J. Okay, now why is subscript 0? A very subtle point. And again, we do the easy model. We won't have to worry about this, but it turns out that if you have firing costs, it adds another friction to the model. So if you hire a worker, you're sort of sitting vis-a-vis this worker, and the worker knows that once you hire the worker and you have to dissolve the match, you have to pay the firing tax. Okay, but before you actually negotiate the wage, before you actually sign the contract and become married, you can negotiate a wage that doesn't reflect that because you don't have to pay that tax. You can always walk away from that worker. So there's going to be a subtle difference between when the ink is dried after the contract is signed, and then after you're in the contract, then you're basically subject, the worker has that extra bargaining power, or it's not bargaining power, the fallback position is enhanced by the fact that if the worker and the firm split up, the firm has to pay this firing tax to the third party, the lawyer, whatever. Okay, so this is I know this is difficult, but we'll come back to this and discuss it again. So the second equation is the valuation of the worker from the position of having a job. So the worker has this valuation capital W. I think of that as its capitalized value. So the implicit flow of income from that must be, by an arbitrage argument, is equal to the right-hand side is the wage I get, given my productivity right now, which is X, it's the state. Remember, the worker and the firm in a match have this value of X that they've inherited from history. They start at 1 and then things start rolling. And then, given that I'm working for this firm, I get W of X, and then I've got, we've assumed away, they assume away income taxes. So the firm pays all the taxes. That's the first equation. So the second part is the probability, that a shock occurs that leads to another value of X that is still in the acceptable region between R and 1. Okay, so we're going to integrate. We know the density, so we're going to integrate over these possible values of W, always conditioned on the value of that this productivity can take. So we use the dummy variable of integration Z. So we integrate over V, W of Z minus W of X. Okay, so that's kind of the change. And this could also go it could go in the negative direction. You might have a fairly high value of X, and then you get a draw, but you get a draw with some probability that's less than X. So that's going to be kind of a loss, but still acceptable to stay in the match. You're not going to quit. So that's, again, the key part of this Morton's and Pisarides modification is that things can happen and you still don't break up. I told you, we learned that you have bad breath. You learned that I don't clean up or don't do my laundry. But we still love each other enough that we stick together. But at some point, it may just fall underneath R, and then we break up. Okay, that's the logic of this wonderful model. So the last part is the probability that x does change in the next instant with probability lambda, and then this is probability that the value of x is below the threshold value, so we break up. And what happens when we break up? As the worker's perspective, I get u. Okay, and I lose w of x. That was the capital loss that Lucas talked about in the first lecture. So my capital loss is u minus w of x. Okay, so if my x going into that equation in that period was close to r, the capital loss isn't so bad. But suppose I just got married and x was equal to 1, okay, and then suddenly, bam, I get hit by a terrible shock, so I have a huge capital loss. So this can all happen, and this is the amazing thing about this model is that these equations, although they look very heterogeneous, actually are, until you start asking what is the distribution of productivity in surviving matches, it's fairly easy to do. Okay, so we can just bear with me for 5 minutes. You can use the diagram. You can use it like the Pisker diagram, except it's called a Morton-Pisker diagram, relating the reservation value to tightness in the labor market. So we'll have a R theta space instead of VU space. Okay, we'll do that probably next week. We'll have to. But the last thing I want to tell you before we leave is the wage. Okay, the wage is negotiated in the same way that we determined the Pisker model. It's a match solution. And what falls out of that is a reservation value of productivity. So R, you can see it in this third equation. I'll elaborate that next time. Is basically that R is an endogenous variable. R will be basically the mutually agreed cutoff level where after we get this Poisson incidence and productivity X is low, then we break up. Okay, so there will be mutually agreed dissolution of the match. Okay, and you can see what's going to determine that. For existing matches, what's going to matter is when the worker's value of employment is very close to U, we hang it up. Okay, so remember what I said before? W is an increasing function of X. The higher X is, there's more there is to share, and the lower X is, the less we have to share. At some point, X is so low that it's at U, and I'm just miserable. It makes sense from the firm's perspective as well, but of course from my perspective, I would never take a job that offered me less value than the value of unemployment. Okay, so that's the last equation in that five-sum. Okay, the last equation in the third line of that slide says basically it's kind of the reservation property will be such that from the worker's perspective, the cutoff probability will never put me in a situation of working for less than the value of being in unemployment. This is not necessarily the case in a general model. So you can imagine a person might take an apprenticeship and work for really low wages. Okay, you might have very low productivity because of some prospective development. Don't have that in this model. Everyone's the same. Ex ante before you enter the match, and then of course this process happens, and the process is the same, even though the outcomes are not the same for all workers. Next time we'll talk about wage determination in this setup. And I tell you, Thomas will give you the simple version of this. My goal is to show you that it's a very powerful tool for looking at lots of different interventions in the labor market, which are very important, especially today. Okay, see you next week.